6.2a is all about solving a triangle. And what does that mean to solve a triangle? Well, it means exactly what our lesson goal is. To solve a triangle is to find all of the angles and all of the sides of any triangle. Today we're only going to talk about right triangles, and then later on we're going to talk about a generic triangle. In order to do this, we're sort of going to exploit a couple of facts or a couple of things to our advantage when we work with right triangles. So, I don't know, call these facts or ideas. Because we're working with right triangles, quote, unlock the usage of trig ratios. Remember the SOHCAHTOA, sine, cosine, and tangents? Those are ratios based off of side lengths of a right triangle. Because we are dealing with right triangles, we can use sine, we can use cosine, so on and so forth. Also, since by definition of a right triangle, one angle will always be 90 degrees, or pi has radians. Thus, the other two angles always add up to 90 degrees, or pi has radians. This is only true for right triangles. In a generic triangle, I have no idea what any two angles may add up to, but specifically in a right triangle, I know for a fact that the sum of the two non-right angles are always 90 degrees. Before we dive into some examples, let's go ahead and review our trig ratios, because, trig was a long time ago. It was before Christmas break. So let's review some terminology. Oh, this thing doesn't make right triangles, so I guess I'll have to do it the hard way. Delete. So for any given right triangle, say here, we have certain names to the side lengths. Now the hypotenuse will always be the side opposite to the right angle. Now, terms like adjacent or opposite is always dependent on what angle you're looking at. So if I'm looking at, say, this angle here, then the side that doesn't create the angle is what we call the opposite. And then the side that does create the angle, that's not the hypotenuse, is what we call the adjacent. But of course, these terminologies flip-flop if you were to look at, say, another angle. So relative to phi here, the angle on top, this is the opposite, and this is the adjacent. But assuming you have the right terminology down, then the trig ratios are defined as follows. Sine of any particular angle, I'll use the theta symbol, but it could be any angle you want, is always the opposite length divided by the hypotenuse. Cosine is always the adjacent length divided by the hypotenuse. And tangent is always the opposite length divided by the adjacent length. And then the reciprocal functions, not surprisingly, are the exact reciprocals. So the reciprocal of sine is cosecant. That's going to be the hypotenuse over the opposite. Secant, which is the reciprocal of cosine, is just the hypotenuse over the adjacent. And then the cotangent, which is the reciprocal of tangent, is the adjacent over opposite. If you know these trig ratios, then you should be able to solve any right triangle I give you, because all it is a matter of looking at the information that's given and seeing what trig ratio relates to the information. For example, suppose I asked you to solve the triangle, and this is the triangle that I gave you. Here's A, B, C, and this is a 12, and this is 30 degrees. So that's all the information you are given. So I hope it's very clear if in this particular picture we are asked to solve for side length A, side length B, and angle B. Notice by standard convention that the side lengths are labeled opposite to the angle. Capital letters are used for the angles, lowercase letters are used for the sides. If they give you an angle in a right triangle, it's always easy to find the other angle. So here's the idea. We know that angle A plus angle B must equal 90 degrees. I mean, that's the idea from above, that the sum of the two non-right angles must equal 90 degrees. Therefore, we should automatically know what angle B is, right? What plus 30 degrees is 90 degrees, or I sort of, slipped up and told you the answer. So angle B should be 90 degrees minus 30 degrees, which is 60 degrees. So that's the first bit. That should have been the easy bit part. Now I'm going to look to solve for A and B. Typically, you do not want to solve for both unknowns at the same time. So let's pick one side length to solve for. Let's go alphabetical. Let's solve for A. So your idea is to focus on the side you're solving for in addition to the information you are given. I know we solved for angle B, but I typically do not want to use solved numbers. I typically always try to use given numbers as much as possible because they're more exact. So at side A, what numbers were we given? We were given 30 degrees, and we were given this 12. Now I ask myself, relative to the angle, in this case 30 degrees because I highlighted it, what side lengths, opposite, adjacent, hypotenuse, am I given? Well, I hope it's not hard to see that relative to this angle, side A is opposite, and side 12 is the hypotenuse. So I think to myself, okay, opposite, hypotenuse. Which trig ratio utilizes opposites and hypotenuse? Well, both of these guys here uses opposites and hypotenuse, and truthfully, I'll go ahead and use these guys as much as possible. Right. So it's based upon this picture. It is a fact that sine of 30 degrees equals A over 12. And then you just go ahead and solve for the letter, right? To get A by itself, multiply both sides by 12. I notice that 30 degrees is a special angle. Hopefully we remember from, Unit 5 that sine of 30 degrees is 1/2. So A is 6. And then you do the same thing for letter B. You ask yourself, okay, focusing on letter B and the information that you're given, which trig function can I make? Well, looking at angle 30, we have B, which is the adjacent, and we have 12, which is the hypotenuse. Adjacent, hypotenuse, adjacent, hypotenuse. Oh, that's going to utilize cosine. So you just go ahead and write down a true statement. It is true, based upon this picture, that cosine of the angle, 30 degrees, is adjacent B over the hypotenuse 12. And then you just go ahead and solve it like a regular equation. Multiply both sides by 12. Me being a good trig student, I should know that cosine of 30 degrees is radical 3 over 2. And then, of course, that's 6 radical 3. Right? So there we go. We solved this triangle. And that's what it means to solve a triangle, is to find all of the missing pieces. Now, sometimes they may not give you an angle, but that's okay, because we have this sort of idea from Unit 5, right? Because a trig ratio always uses 2 out of 3 sides of a right triangle, we can always quote unlock any triangle if we have a trig ratio. Of course, the question is, how? Right? How is that possible? Why is knowing 2 sides out of 3 of a right triangle, if I'm given a trig ratio, how does that unlock the entire triangle? Well, recall this very wonderful and oh so important theorem in the world of mathematics, in the world of geometry. That is Pythagoras' theorem. Pythagoras' theorem states the sum of the squares of the legs of a right triangle is equal to the square of the hypotenuse. Or if you are not a written type of person, the famous formula a squared plus b squared equals c squared, assuming c is the hypotenuse. Because we have Pythagoras' theorem, which utilizes all 3 sides, a trig ratio will always give you 2 out of the 3 sides, which means if you know a trig ratio, you can always use Pythagoras' theorem to solve for the missing side. And that is important because that will allow you to figure out basically all of the trig ratios. This Pythagoras' theorem is sort of like the linkage that connects sine, cosine, tangents, and all of the other trig ratios. So that'll allow us to do problems like this. Given that tangent of theta equals 4/7, find the other 5 trig ratios of theta. What the heck does that mean? Basically, it's saying, hey, I'm going to tell you that tangent of theta is 4/7. Well, what's sine of that theta? What's cosine of that theta? What is secant of that very same theta? Now, this seems like a very hard question. I mean, I have a variable. I don't know what the angle is. How am I supposed to figure out the sine of an angle that I don't have a number for? Well, the problem explicitly gave you a valid trig ratio. Tangent of that theta is 4/7. Let's visualize this. Because it's using tangent, I know some right triangle has to be involved. I don't know what it looks like, so I'm going to do a quick sketch here. Now, I don't know where this angle theta is, so I'm going to place it somewhere convenient. Let's just put this theta down here. Well, what do I know about this picture here? Well, I know that tangent of this angle here is 4/7. And knowing my SOHCAHTOA ratios, knowing that tangent is opposite over hypotenuse, I know for a fact that the opposite side of this angle has to be 4. And I know for a fact that the adjacent side of this angle has to be 7. So I can immediately, in this picture, fill out 4 and 7 here. What do you know? I have 2 out of the 3 sides of a right triangle. I can use Pythagoras' theorem to figure out the rest of the missing third side. So from this picture, we know, let's call this, I don't know, x or something. We know 4 squared plus 7 squared equals x squared. And then this should be a relatively simple problem to solve. 4 squared is 16, 7 squared is 49, 16 plus 49 is 65. And then I'd take the square roots. Now, since I'm solving for a side length, It doesn't make sense for a side length to be negative, so it should be plus or minus because I'm taking a square root, but it's only going to be the positive square root of 65 because I want a length here. And I do not think we can simplify 65. So that's what, 5 and... No, we can't. We can't simplify that. So there we go. I know for a fact that this is radical 65. Now, with looking at this picture, I hope it's very easy to read the trig ratios. So this tells us I don't need to know what the angle is. Is it 27 degrees? Is it 58 degrees? Who cares? I don't know. Now that I have all three sides of the right triangle, now we can read that sine of the theta opposite over hypotenuse is just 4 over rad 65. Cosine of the theta adjacent over hypotenuse is 7 over rad 65. I don't have to do tangent because they already said tangent. They already gave us tangent here. Cosecant of theta is just the reciprocal of sine, rad 65 over 4. Secant of theta is the reciprocal of cosine. It's rad 65 over 7. And then cotangent of theta is the reciprocal of tangents, 7/4. So this is what I mean by having a single trig ratio. This is the only information we were given, but it unlocked the entire triangle. It gave me access to every single other trig ratio thanks to Pythagoras' theorem. Okay. So that's the idea with these types of problems. If you're given a trig ratio and you want to find the others, just draw it out and then use Pythagoras' theorem to find the missing sides. This is sort of just a bonus question. I added this to the notes just to emphasize that, you know, all the examples that we've done are pretty wimpy, simple, pretty straightforward. Sometimes you might need to take 2 or 3 or 4 steps to solve a problem completely. So for example, suppose I asked you to find x rounded to the nearest 10th place. That's 1 decimal place. And you were given this picture. And I tell you that this right here is x. This right here is 30 degrees. This right here is 6 degrees. This right here is 85. Now, to solve for x, you first figure out where x is. So clearly, it's marked for us. This is x here. Now, up until now, we've only been working with right triangle trig. So I need to make sure that the side length that I'm solving for is part of the right triangle. Now, I hope we can see that, unfortunately, in this case, x is a part of this triangle. And that, even though it's a sketch, it's not drawn to scale, I know that that is not a right triangle. Nothing indicates it as such. So this is a problem. So when the side length that you're solving for is not part of a right triangle, you have to ask yourself, is the thing that I'm solving for a part of another side that is a part of a right triangle? And I hope we can see that this x here, this length here that I'm solving for, is a part of this length, which combined with this side is a part of a right triangle. So I know for a fact that although this is the x I'm solving for, I should be really looking at this entire triangle because it is a triangle that is a right triangle. And I can use SOHCAHTOA, I can use trig ratios when I have right triangles. Here's the problem. I can use SOHCAHTOA to figure out this whole side length here. But our ultimate goal is to solve for sorry about that, technical difficulties. Our ultimate goal is to solve for this side length here. Well, if I can use trig to solve for the whole side length, and I want to solve for this length, I need to subtract the yellow length. But the yellow length isn't labeled, it isn't marked. So guess what? I have to call it another variable. So in this case, we're working with 2 variables. Let's call this length whatever we want. It doesn't really matter what letter we use. Let's I don't know, let's call it A, just because it's the first letter of the alphabet. So before I can even solve for x, I need to solve for a. Well, again, focus on the side length that you're looking for and ask yourself, is it a part of a right triangle? And indeed, a is part of a right triangle, this smaller right triangle, and then I can use trig to solve it. So focusing on that right triangle, I ask myself, what information do I have? I have this 85, I have this 60. So relative to this angle, opposite, adjacent, hypotenuse, what are we working with? Well, relative to the 60, this is an opposite side. This is adjacent side. I know opposite, adjacent, that has to be tangent. So we can see that the tangent of 60 degrees is 85 over A. And then this gives me an equation to solve for A. So let's multiply both sides by A. Divide both sides by tangent of 60. And because 60 is a special angle, me being a good math student, I know that tangent of 60 is, what's that one, is radical 3. So great, I've solved for A now, but again, A is not what I'm looking for. I'm looking for X. Now X, again, is a part of this bigger right triangle. This bigger right triangle here. So I need to focus on this big right triangle. Well, what information do I have? I have this angle. I have this side length, and I'm working with this entire side length. And it just turns out that relative to this angle, we have tangent again, because this is opposite and this is adjacent. So working with that big triangle, I can say tangent of 30 degrees is the opposite 85 over the adjacent side, which again is x plus a. Now we figured out what a is. I typically like to do the substitution last, so I'll leave it as a plus x, even though I know what a is, just to make the writing easier. So we then go ahead and solve. So I'm going to multiply both sides by a plus x. So that's tangent of 30 times a plus x equals 85. Let's go ahead and distribute. Tangent of 30 times a plus x times tangent of 30 degrees equals 85. I'm solving for x, so I'm going to subtract this guy because he doesn't have any x's. X tangent of 30 degrees equals 85 minus a tangent of 30 degrees. And then the last step to solve for x is to divide out that tangent of 30. And then you can go ahead and plug in all the variables and all the special trig ratios. So 85 minus, we said a was 85 over radical 3. Tangent of 30, just knowing my special trig values because I'm a good trig student, is 1 over radical 3 over 1 over radical 3. Right. And then it's just doing simplification. This is arithmetic. This is algebra. So what does that give us? That gives us 85 radical 3 minus 85, right? And of course, if you were to pop that guy into your calculator, you're going to get about 98.1, right? So that's it. That's I mean, I don't think it was a difficult question. It just requires you to do multiple steps. But that's how you use trig ratios to solve right triangles. And again, the idea is if you know one trig ratio, you've unlocked the whole triangle because of Pythagoras' theorem allows you to figure out all three sides. So that's what the first half of 6.2 is. Can you completely solve a right triangle? Good luck.